Welcome to the video on the Module 2 PN junction. So in this video, we will be discussing about what is meant by a PN junction, what is meant by forward bias and reverse bias junction, what is a qualitative description of the current flow in the junction. So that is, we will be discussing what are the different components, current component in the junction, and we will discuss what is meant by reverse bias. So in reverse bias, we have an important concept called as reverse bias breakdown. So here we will be discussing what are the two types of breakdown mechanism, that is Zener and avalanche breakdown. Followed by that we will be seeing what is meant by a rectifier and what characteristics the device should possess to be a good rectifier. So in the second part of this module 2 we will be discussing about the optoelectronic devices. So here we will see what is meant by an illuminated junction. So what happens when a light ray falls on the semiconductor material when it is reverse biased or forward biased. So based on its use, we will be discussing what is meant by a solar cell, what is meant by photodetectors, what is light emitting LED and light emitting materials used for the LED. So here, when I come to this first module, we have discussed what is meant by a PN junction. So in that, we have discussed what is an extrinsic semiconductor, how an extrinsic semiconductor works. So there we have seen two types of material. One is called as P-type material, and another one is called as an N-type material. Now, how an PN junction is formed? A silicon PN junction, it can be formed or it can be realized by formation of a junction between an N-type and a P-type doped region. That is, the junction is formed by process like implantation or diffusion of dopants in a wafer. So the wafer is a pure semiconductor material which will be used as the base of my device. So when I dope it with a pentavalent impurity, I will be getting an N-type silicon. So here in this example, we can see that a silicon PN junction is formed by having an N-type silicon wafer. That is, already the base is an N-type in which we will be having an P-type material doped to it. So based on the depth, based on the material present here, I can say about the depth of the device, that is the donor and the acceptors. Acceptors are nothing but the P-type silicon formed, that is, it is formed by diffusion of the boron atoms, and here the N-type is nothing but doped due to the phosphorus. So here this gives me the charge carriers available. So here the P plus indicates that the P region is heavily doped when compared to the N region. So the significance of these things we will be studying in the forthcoming videos. So here when I take an P region, we have in the previous class we have understood what is meant by a Fermi level. So a Fermi level is nothing but it gives the average occupancy of the electron, the occupancy of the energy state of the electron in a system. For example, if I take a P-type semiconductor material, the Fermi level will be near to the valence band, and if I take an N-type material, the Fermi level will be near to the conduction band. So when they are separated and when they are uniformly doped, so these two Fermi level are found to be straight, or it is said to be a constant, and it gives me a homogeneous junction, and the Fermi level of both the silicon material is constant. So the semiconductors are said to be in the thermal equilibrium. So thermal equilibrium is nothing but the state at which my Fermi level is constant throughout my device. So now when I combine a P and N region, so what happens? So we know that P-type material, the majority carriers are the holes, and in N-type material, the majority carriers are electrons. So when a P and N are brought together, diffusion of charge carriers takes place due to the concentration gradient. That is, there will be a rate of change of concentration of the charge carriers on the two layers, and when they are brought together they will try to equalize. That is, the holes in the p region will try to move towards the n region, and similarly the electrons from the n region will try to move towards the holes. So we know that when electrons and holes are put together, they will get recombined. So what happens is, at the interface, at the junction, so the electrons which is crossing the junction and coming to the p region will try to recombine with the holes, and similarly the holes which is moving through the junction will get recombined at the n region. So at the near region of the junctions, so the electrons and holes will be getting recombined, and it will leave us only the immobile ions. Immobile ions are nothing but the positive and negative charged donors and the acceptors. So here, because of the immobile ions, an electric field is created. So electric field is such that the n-type region will be having positively charged ions, and the p-type region will be having a negatively charged ions, and hence an electric field will be formed in this direction. So what happens because of this electric field? So this electric field will stop the further movement of the electrons and the holes through the junction. So we understood that the majority carriers constitute a current which is called as the diffusion current, and that it will be get compensated, or it will be the diffusion current will be it will be stopped, or I can say that the diffusion of the charge carriers may be stopped due to the developed electric field. Now, even though there is a diffusion current, and when my P and N junction is formed with zero bias, that is zero bias, my Fermi level will be constant throughout the device, and hence the device is said to be in thermal equilibrium. So how this thermal equilibrium happens? So this will give me the new concept called as drift. So what is meant by drift? So because of my developed charge carriers, or because of the developed electric field here, even though it opposes the flow of majority carriers, this positive charge will try to attract the electrons from the p region, and similarly then this negative charge will try to attract the holes from this. That is, the minority carriers movement will be happening because of the developed electric field, and hence there will be movement of minority carriers. So in that case, free carriers get removed from the from the space charge region, depletion region, but there will be movement of positive, I mean majority carriers, which results in the whole diffusion current, and similarly there will be movement of minority carriers, which will result in the drift current. So put together, I can say that at zero bias, there will be two types of current. One is called as drift current, and another one is called as diffusion current. And we know that these both the current will be of opposite direction, and hence at thermal equilibrium or at zero bias, the whole diffusion current and drift diffusion current cancel each other, and similarly electron diffusion current and electron drift current will cancel each other. That is given here. That is, the current density will, due to the electrons, will be equal to zero. That is, the drift current will be equal to the minus of diffusion current, and similarly for the holes also, the drift current will be equal to minus of the diffusion current. This can be used to derive the equation for the current of an PN junction. So as we can say that at thermal equilibrium or at zero bias, there will be zero current, and there will be zero potential difference will be created there. So in the next video, we will be discussing what is meant by forward bias and reverse bias of a PN junction diode. Thank you.